For decades, humanity has depended on space-based observatories, Hubble, James Webb, Chandra to reveal the universe with a level of clarity impossible from Earth's surface. But something unexpected has changed that narrative. A telescope still rooted on Earth, still peering through our planet's atmosphere, has produced images so expansive, so detailed, and so unexpectedly deep that astronomers worldwide paused in disbelief. For the first time, the Vera Rubin Observatory has truly opened its eyes. And what it captured on its very first night is not just beautiful, it is deeply unsettling. It reveals a sky so dense, so active, and so alive with motion that it challenges how we have long mapped the cosmos. But now, something unexpected has happened. A telescope still anchored to the ground, still breathing Earth's atmosphere, has delivered images so vast, so detailed, and so shockingly deep that astronomers around the world stopped what they were doing. Because for the first time, the Vera Rubin Observatory has opened its eyes. And what it saw on its first night isn't just beautiful, it's unsettling. It's a glimpse into a sky so crowded, so dynamic, so alive with activity that it threatens to rewrite how we map the universe. A camera the size of a small car capturing 3.2 billion pixels at once. A single exposure wide enough to hold 40 moons. A dataset that will grow so massive it will take lifetimes to interpret. And yet, the very first images already contain secrets. Merging galaxies, newborn stars, tens of thousands of ancient clusters, and more asteroids in 10 hours than the rest of humanity found in weeks. This is the moment astronomers have waited for. A machine powerful enough to watch the sky change, to catch cosmic events in the instant they happen, to reveal structures we didn't even know existed. Tonight, we're diving into what the Vera Rubin telescope has just seen and why its first images have shaken the scientific world. Long before the first images were released, the Rubin Observatory was already a legend waiting to be born. Perched atop Cerro Pachón in Chile, one of the driest, clearest, darkest places on Earth, it was designed not just to take pictures, but to survey the universe in a way no other observatory ever has. Its heart is the Simone Survey Telescope, a three-mirror design unlike typical two-mirror systems, giving it a sharpness and field of view unmatched by telescopes of its size. The primary mirror alone spans 8.4 meters. But what truly sets Rubin apart is the fusion of its optics with the largest digital camera ever built. This camera weighs nearly 3 tons, stretches 3 meters long, and captures ultraviolet, visible, and near-infrared light with stunning precision. But where Rubin begins to defy expectations is in its scale. One image covers 10 square degrees, an area equivalent to 45 full moons. In a single snapshot, Rubin sees what would take Hubble thousands of images to assemble. And as it completes its scans every 3 days, it doesn't just produce static portraits. It builds a time-lapse movie of the universe, exposing the flickers, pulses, collisions, and transformations happening all around us. This is not a telescope built to look at one object. It is built to look at everything all at once. When Rubin captured its first images in June 2025, astronomers expected something impressive, but they were not prepared for what the observatory actually delivered. After just over 10 hours of test observations, Rubin produced a mosaic that the scientific community quickly nicknamed the Cosmic Treasure Chest, a breathtaking 25-square-degree portrait of the southern Virgo cluster, the closest large galaxy cluster to the Milky Way. This image, stitched together from 1,185 exposures, contains millions of stars and galaxies. Spiral galaxies stretch their arms lazily across space. Merging galaxies twist together like cosmic smoke. Filaments connect distant clusters in web-like structures. In the background, barely visible unless you zoom in, lies a sea of faint reddish galaxies, each one a possible host to billions of planets. And this overwhelming richness represents just 0.05% of what Rubin will detect. The observatory is set to reveal 20 billion galaxies, and this first mosaic is just the preview. The trailer for a decade-long film The Universe is about to broadcast through Rubin's lenses. As astronomers explored the mosaic, they found not just beauty, but unfiltered cosmic evolution. Structures forming, interacting, fading, and expanding, captured in detail so immense that it reshapes our understanding of what a first image can be. If the first mosaic demonstrated Rubin's power, its next release proved something even more astonishing, that a ground-based telescope could rival space observatories in depth and scale. The Rubin team unveiled a wide-field mosaic of the Lagoon Nebula, a star-forming region about 5,200 light-years away. Normally, when we see the Lagoon Nebula, it's through narrow, zoomed-in images from telescopes like Hubble. But Rubin showed us something else entirely. A panorama where the nebula, despite spanning 55 light-years, occupies only a fraction of the frame. Surrounding it are countless points of light. Open clusters like Messier 21, the glowing Trifid Nebula, Bochum 14, and the densely packed globular cluster NGC 6544. In a single image, Rubin captured structures that exist at wildly different distances and scales. From newborn stars in the nebula's core to ancient globular clusters thousands of light-years further away. This is the consequence of Rubin's staggering field of view. Hubble sees 1% of the moon's surface in a single image. Rubin sees 40 moons at once. And yet, even with this immense view, its details remain sharp, intricate, and layered. For the first time, we see the lagoon not as an isolated object, but as a connected piece of a much larger cosmic landscape, a neighborhood filled with birth, death, chaos, and motion. A star at the edge of the image is just as sharp as one at the center. Its robotic arm system swaps filters at remarkable speed, allowing the observatory to transition between ultraviolet, visible, and infrared observations effortlessly. The result is not a photograph in the traditional sense. It is a multidimensional data tapestry. Every exposure contains layers of information invisible to the human eye: chemical signatures, thermal clues, spatial distortions, and motion trails. Rubin doesn't just take pictures. It extracts the universe's hidden structure frame by frame. While the Hubble Space Telescope captures images at an extraordinary level of detail, its field of view is tiny, equivalent to just 1% of the moon's surface. It is engineered to zoom into cosmic objects like galaxies, nebula, or star clusters, revealing narrow regions with microscopic precision. Rubin, however, was never designed for close-ups. With its 8.4 m primary mirror, vast camera, and sweeping optical system, its purpose is scale. One Rubin image can capture a sky area equal to 40 full moons. That means Rubin exposes cosmic context, the relationships between galaxies, the filaments connecting clusters, the sprawling architecture of nebulae. When you compare Rubin's wide-field Lagoon Nebula mosaic to Hubble's tight portrait, the difference is almost shocking. Hubble sees a window. Rubin sees the entire landscape around it. Hubble allows us to study the anatomy of a star-forming region. Rubin allows us to understand how that region fits into the galaxy's ecosystem. In this sense, the two observatories are complementary. One is a microscope. The other is a panoramic drone soaring above the cosmic terrain. And Rubin's first light images prove that the universe looks very different when you finally step back far enough to see the bigger picture. Skyviewer.app isn't just an educational tool. It's an invitation for anyone, anywhere, to explore data that would once have been accessible only to professional astronomers with high-performance computing systems. Because Rubin's images are so enormous, some built from over 1,000 exposures, zooming through them feels like moving across a living map of the universe. A user can dive from wide cosmic landscapes into clusters, down into individual stars, and then out into galaxies that appear as faint specks only when viewed at full resolution. The platform is the beginning of something revolutionary, a world in which citizen scientists and enthusiasts participate directly in discovery. Hidden supernovae, rare stellar pulses, faint comets, even interstellar visitors could be spotted first by someone scrolling casually through Rubin's mosaics. Astronomy is becoming democratized through Rubin's openness. And with half a petabyte of data coming each year, the scientific world will need all the eyes it can get. Astronomers estimate that one interstellar object passes through our solar system every year. But until recently, we lacked the capability to detect most of them. Objects like Oumuamua and 2I/Borisov were found almost by accident, slipping past our instruments with only days or weeks of visibility. Rubin changes that. Its wide field of view and rapid 3-day scanning cycle mean it can pick up faint, fast-moving objects long before they get close to the sun, precisely the window of time when they're easiest to study. In its very first test run, Rubin identified over 2,000 new asteroids, including several near-Earth ones, demonstrating that it is already capable of spotting unusual trajectories. For interstellar science, this is transformative. Rubin may detect dozens of interstellar visitors during its decade-long survey, giving scientists the chance to analyze their composition, structure, and motion in real time. These objects are snapshots of other solar systems, material forged around alien stars, carrying chemical histories we've never encountered before. Rubin could therefore become humanity's first reliable gateway to studying the raw debris of distant worlds. And with enough detections, researchers may even begin to answer questions that Oumuamua raised but never resolved, including whether some of these visitors are entirely natural or not. In the end, what the Vera Rubin Observatory has revealed in its very first images is not simply a new chapter in astronomy. It is the beginning of an entirely new language for understanding the universe. For decades, our vision of the cosmos has been shaped by narrow windows, tiny fields of view, single snapshots, isolated regions of space studied one at a time. But Rubin breaks that paradigm completely. Its first images already show us that the sky is not a quiet dome sprinkled with stars. It is a dynamic tapestry in constant motion, overflowing with structure, evolution, and phenomena we've barely begun to classify. A single mosaic captures millions of galaxies at once. A 10-hour scan exposes thousands of asteroids we didn't even know existed. A wide-field view of a nebula reveals not just a star-forming region, but the cosmic neighborhood surrounding it. A cradle of gas, clusters, filaments, and ancient stars stitched together across unimaginable distances. Rubin doesn't just collect data. It compresses the living universe into a format we've never seen before. A time-lapse of existence itself, updating every 3 days, building a cosmic memory that will grow to 500 petabytes by the end of its mission. It is a machine designed not just to observe, but to anticipate, capturing events the moment they happen. Supernova erupting, gamma-ray bursts detonating, celestial visitors streaking in from other star systems. For the first time, we are watching the sky the way the universe intended, as something alive, dynamic, unpredictable, and endlessly evolving. And Rubin is only at the beginning of its journey. Its wide-field precision is already rewriting the rules of astrophysics. Its scanning cadence is redefining how we detect interstellar objects. Its RR Lyrae detections are mapping the skeleton of the Milky Way. Its unprecedented images are bridging the gap between professional astronomers and the public, allowing anyone to zoom through the cosmos with tools once reserved for experts. Rubin is not just a telescope. It is a shift in perspective, a signal that the era of static astronomy is over and the era of cinematic astronomy has begun. And when we consider what this means for the next decade, the discoveries, the surprises, the cosmic alarms that Rubin will set off, we realize something profound. This telescope will change what humanity knows about the universe more in 10 years than we learned in the last 50. Everything is about to accelerate. Everything is about to expand. The universe has never been more ready to reveal itself, and we've never been more prepared to see it. If you want to follow every discovery Rubin makes, every asteroid, every supernova, every interstellar visitor, every cosmic shockwave, make sure to subscribe, turn on notifications, and stay with us because the next image Rubin sends might not just change astronomy, it might change the world.